In this module, we are going to define the number pi using the trigonometric functions and calculus. So we already know that sine squared x plus cos squared x is equal to 1. This immediately gives us the following inequalities: minus 1 less than or equal to sine x is less than or equal to 1, and minus 1 less than or equal to cos x is less than or equal to 1. Now, we already know from our familiarity with the trigonometric functions that all values in between minus 1 and 1 are indeed taken by both sine and cos, but we have not yet proved that rigorously. So first, let us try to prove that there is a point x in R such that sine x is equal to 1. Okay. Equivalently, because sine squared x plus cos squared equal to 1, we must have cos x equal to 0. Both are equivalent. Sine x equal to 1 if and only if cos x equal, oh, this is not exactly, sine x could be minus 1. So if sine x is 1, you have cos x is 0. Okay, this side implication at least we have. Now, first of all, observe that derivative of sine x at x equal to 0 is equal to 1. Okay, and we also know that sine 0 is 0. Because the derivative of sine is cos and cos is a continuous function, the derivative of sine is certainly positive when x is near 0. Because the derivative at 0 is 1 and the derivative is cos x, which is a continuous function, the derivative is positive when x is near 0, which means sine is increasing, in the vicinity of 0. Okay. So sine is going to be an increasing function near 0. This means sine x is greater than 0 when x is greater than 0 and x is close to 0. Right? Because sine 0 is 0. Because of that, sine will be increasing. And therefore, sine x will be positive. Okay. Now, suppose for all x in R, cos x is never 0. Suppose cos x is never 0. We also know that cos 0 is 1 and cos x is never 0 and cos is continuous. Putting all this together by intermediate value property of cos, it must be the case that cos x is greater than 0 for all x in R. Right? So what does this tell us? This tells us that d by dx of sine x is greater than 0 for all x in R, which just means sine x is a strictly increasing function on the whole of R, not just near the vicinity of 0. Sine x is a strictly increasing function for all x in R. Okay. Now, we are going to manipulate sine and cos using these trigonometric identities that we have established in the last module to derive what we need. Okay. So fix a greater than 0. Fix a greater than 0. We know that because cos is positive, 0 is less than cos 2a. Because we have just under the assumption that cos is never 0, cos is always positive, so 0 is less than cos 2a. But from the trigonometric identities that we saw last time, cos 2a is nothing but cos squared a minus sine squared a. Okay. Now, because sine is strictly increasing for all x greater than 0, cos must be strictly decreasing for all x greater than 0. because cos squared x plus sine squared x is equal to 1. Keep that in mind for the moment. We have also seen that if a is greater than 0, sine squared a must be positive, simply because sine is strictly increasing whenever, in fact it is strictly increasing throughout R, and sine 0 is 0, so sine squared a is going to be a positive quantity. And because sine squared a is positive, this will be strictly greater than cos squared a. Note, I am using the fact that sine a will never be 0 when a is greater than 0, because sine is a strictly increasing function and sine of 0 equal to 0. Okay, sorry, this will be less than cos squared a. Sorry, I completely reversed the inequality that I need. Okay, now inductively we can show that cos 2 power n a is less than cos a the whole power 2 power n. Okay, and this will be true for all n in the natural numbers. Just inductively apply the argument that we have given now. Okay, this means as n goes to infinity, cos 2 power n a converges to 0. Okay, this happens because we already know that cos a is definitely going to be strictly less than 1. Why do we know that cos a is going to be strictly less than 1 when a is greater than 0? Because sine is an increasing function. Sine a will be non-zero and positive, so cos a cannot be 1. Okay, so cos 2 power n a approaches 0. Okay, now because sine is strictly increasing, cos is strictly decreasing, we can use the fact that cos 2 power n a goes to 0 to conclude that limit x going to infinity of cos x itself is equal to 0. Okay, justify. This is fairly easy because the key step is the fact that cos is strictly decreasing. Okay, now because limit x going to infinity cos x is equal to 0, we can find some b greater than 0 such that cos b by 2 is less than 1 by 4. Okay, and because cos b is less than 1 by 4, we can find some b greater than 0 that cos b is less than 1 by 4, and it's clear that whenever cos b is less than 1 by 4, sin b definitely has to be greater than half. In fact, you can get a better bound, but that's all I need. Sin b is definitely going to be greater than half. Okay, how does this help us? Well, again you apply the identity cos 2b is cos squared b minus sin squared b. Okay, but cos squared b minus sin squared b, when you substitute 1 by 4 and 1 by 2, this will be less than 0. Okay, but cos is strictly greater than 0 for all x. That's how we started. That's how we started. This is a contradiction. Okay, hence our assumption is wrong. We can find x naught in R. Such that cos x naught is equal to 0. Okay, now what we are going to do now with this is we can define pi the following way. Let let S be the set, let S be the set of all y in R such that cos y is equal to 0. Okay. Okay, in fact, all y greater than 0 such that cos y is equal to 0. In fact, we can find x naught greater than 0 such that this is satisfied. We can find x naught greater than 0 such that cos x naught is equal to 0. Okay. Now, what we are going to do is take C to be the infimum of S. Okay. By continuity, cos C is equal to 0. Okay. And C must be greater than 0 because we know that cos 0 is 0. Sorry, cos 0 is 1. Because of that, C must be greater than 0. What we do is we define C, or rather pi, we define pi to be the quantity by definition as 2C. So essentially what we have found out, the C is nothing but pi by 2, which we are familiar with. Okay. And by the way we have defined things, cos is going to be greater than 0 if 0 less than or equal to x less than pi by 2. That's simply the way C has been defined. Okay. And because of this, sine will be sine x will be 0 less than or equal to sine x is less than 1 if 0 is less than or equal to x less than pi by 2. And we also know that sine pi by 2 is equal to 1. Okay. Now what we are going to do in the next module, now that we have pi, we are going to relate pi and the trigonometric functions and get various identities such as sine x plus pi by 2 is cos x and cos x plus pi by 2 is minus sine x and so on. And using these relations, we are going to somewhat get an approximate graph of the sine and the cosine function. This is a course on real analysis and you have just watched the module on the number pi.